Okay, let's unpack this. Cotton. We all, reach for it. It's that comfy, breathable fabric we love.
Hmm?
But here's something maybe surprising. This king of fibers, well, it has a couple of hidden issues. It's actually quite flammable, and it can be a real breeding ground for bacteria.
Yeah, and those things, flammability and microbes, they're becoming bigger and bigger deals, in our modern world.
Exactly. So for this deep dive, we're going to jump into the, frankly, really fascinating world of eco-friendly solutions. People are trying to tackle these exact challenges.
Right. Creating cotton textiles that are safer, more hygienic.
And, crucially, better for the planet. We're talking sustainable approaches here.
It's really about how science is stepping up, making sure this essential fabric is, well, fit for the future, but responsibly.
And to guide us, we've got this excellent resource. It's a comprehensive review paper, basically pulling together all the latest research on sustainable flame retardant and antibacterial treatments for cotton.
It's a great starting point, kind of a shortcut to the cutting edge.
So the mission, really, is to pull out the most promising, the most intriguing, eco-friendly ideas from this research. We want you to get a clear picture of how science is making cotton better, safer, cleaner, without that heavy environmental cost.
Makes sense. Where should we start? The basics of cotton itself.
Yeah, let's do that. Why is cotton so dominant? Why is it the king of fibers anyway?
Well, it really earns that title. I mean, the comfort is undeniable, right? And breathability. It just feels good against the skin.
True.
Plus, it's incredibly versatile. Clothing, sure, but also home textiles, bedding, towels, even things like medical supplies and industrial uses. And it dyes well, looks good.
It's everywhere, isn't it? And the scale, globally, it's massive.
Oh, absolutely. Economically, it's huge. Supports millions of livelihoods. They call it white gold in some places because it brings in so much foreign exchange.
Wow.
Production-wise, we're looking at something like 27 million tons a year currently.
Yeah.
Expected to hit maybe 29 million tons by 2028.
And who are the big producers?
The main ones are India, China, the U.S., Brazil, and Pakistan. Together, they account for, I think, around 3/4 of the global total.
Okay, so it's vital. But back to the downsides. That flammability, it sounds like a really serious issue.
It is. Cotton is mostly cellulose, and cellulose is naturally, well, flammable. Untreated cotton catches fire easily, burns fast, the flames spread quickly.
And lots of smoke, you mentioned.
Yes, significant smoke production. Makes fires harder to fight, more dangerous. And unfortunately, fires involving cotton materials, furniture, bedding, nightwear are a real concern. Statistics bear that out.
Yeah, you found some numbers in the review.
I did. UK fire stats, for example, consistently show a high number of house fires involving upholstered furniture, mattresses, bedding, often cotton-based, and international data from 2022 pointed to textiles being involved in a significant chunk of fires overall.
Sobering. It really highlights the need for effective flame retardants.
Definitely. Practical, real-world need.
And then there's the other side, the bacteria problem. Why is cotton so susceptible?
It just doesn't have inherent antibacterial properties. So, microbes, bacteria, fungi, they can grow quite happily on it, especially if it's damp.
Leading to smells.
Yes, those unpleasant musty odors, for one. But it can also degrade the fabric itself over time, make it weaker.
And I guess the pandemic made everyone think more about hygiene.
Absolutely. The review points that out clearly. COVID-19 really heightened awareness about microbial contamination, leading to a much bigger demand for hygienic textiles, things that actively reduce germs.
Makes sense. So people want fabrics that do more now.
Exactly.
Yeah.
Multifunctional textiles, that's the trend. And a key combination everyone's looking for is flame resistance and antimicrobial properties, especially for things like home furnishings, protective clothing, medical gear.
Places where safety and hygiene are both critical.
Precisely.
So how did manufacturers used to tackle this before all the eco-friendly focus?
Traditionally, you had two main routes, a two-step process treating for flame retardancy first, then for antibacterial properties, or vice versa.
Okay. Any problems with that?
Well, yeah. The chemicals used for one treatment could sometimes interfere with the effectiveness of the other. They might react badly or just reduce performance.
Ah, okay. What was the other way?
A single-step approach, using complex synthetic chemicals designed to do both jobs at once.
Sounds more efficient.
Maybe, but those dual-action chemicals often came with their own environmental baggage, concerns about toxicity or persistence. That's really where this review picks up the shift towards greener alternatives.
Right. So let's dive into those eco-friendly flame retardants. You mentioned a move away from halogenated ones.
Yes, definitely. Big concerns about halogens like bromine or chlorine impacting health. and the environment. So the focus now is heavily on non-halogenated options, things derived from natural sources, bio-based materials, and certain inorganic compounds.
And you said combinations are often key, synergistic effects.
Very often, yes. It's not always one single magic bullet. It's about finding combinations of these greener agents that work together to give you really effective, durable flame retardancy.
Okay, let's break down the natural or bio-based ones first. The review split them up.
Yeah, broadly into animal-based like chitosan from shells, or even DNA and biomass-based.
Hold on, DNA as a flame retardant.
I know, right? Sounds wild. We'll get back to it.
Okay. Biomass-based first then. What's included there?
Things derived from plants, mostly. Cellulose itself, starch, tannins, phytic acid, lignin, also plant extracts and oils. Lots of options.
Let's take phytic acid. What's special about it?
Phytic acid is naturally rich in phosphorus. And phosphorus is really good at promoting char formation when a material burns.
Char, that black stuff left after a fire.
Exactly. That char layer acts as a protective barrier. It insulates the underlying material from heat and oxygen, slowing or stopping the burning process. Phytic acid helps build a better char layer.
And it improves something called LOI.
Yes, limiting oxygen index. It's a measure of how much oxygen needs to be present for a material to burn. A higher LOI means it's harder to ignite, more flame resistant. Phytic acid, especially combined with other things, can really boost the LOI of cotton.
It's interesting. What about tannins and starch? They sound pretty common.
They are. Tannins are polyphenolic compounds found in lots of plants, tree bark, leaves, fruits. They're generally safe, cheap, abundant. Condensed tannins look particularly promising. Again, those phenolic groups help with char formation.
And starch, like cornstarch.
Basically, yes, though it's usually modified, like ammonium starch, phosphate, ASTP. It's made from biomass starch, contains phosphorus.
How well does it work?
Pretty well. Studies show it can give cotton a really high LOI. And importantly, it seems quite durable. One study found it kept a good LOI even after 50 washes.
50 washes? That's crucial for clothing. How does it stick?
It seems to form strong chemical bonds, covalent bonds with the cotton fibers. And its mechanism is mostly in the solid phase, promoting that char.
Okay. What about the others? Cellulose, alginate, lignin?
They're all renewable, biodegradable polymers. On their own, maybe not potent enough, but they can be used as building blocks combined with compounds containing nitrogen, sulfur, phosphorus, silicon to enhance fire resistance. It's about finding the right chemical partners.
And plant extracts. Sounds like researchers are trying everything.
They really are exploring. Some plant saps or waste products naturally contain phosphorus or positive metal ions that can help. The review mentions things like sap from false banana plants.
False banana.
Enset ventricosum. Also, regular banana pseudostem sap, spinach juice, pomegranate rind. They've all shown some effect, like increasing burn time or reducing char length. Durability varies, though. That false banana sap treatment lasted up to 15 washes.
15 is okay, not 50, but still something. What about waste tea?
That was interesting. An extract from waste tea leaves made cotton self-extinguishing in some tests. It significantly boosted the LOI and reduced the char length compared to untreated cotton.
Why does tea work?
Likely the polyphenols and tannins in the tea. Great for char formation. But again, like many plant extracts, wash durability for large-scale use needs more work.
So it sounds like using these biomass options alone often isn't quite enough. Limitations in durability or effectiveness?
Often, yes. Or they might affect the feel of the fabric. That's why researchers are exploring combinations, mixing different biomass retardants or combining them with other materials.
Like lignin and phytic acid?
Yeah, that was used in a plastic but showed improved performance. Another study combined phytic acid, silk protein, and potato starch for synthetic fibers may be adaptable to cotton, which reduced heat and smoke. It's all about synergy, finding combinations that boost performance and overcome individual weaknesses.
The team-up approach. Makes sense. Okay, let's switch to the animal-based ones. Chiosan first, from shrimp shells.
That's the main source, yes. Chitin is abundant in crustacean shells, insect exoskeletons. Chitosan is derived from chitin. It naturally contains nitrogen, which, like phosphorus, aids char formation.
Is it effective on its own?
It helps, but it really shines when it's modified or combined with other things. Researchers use layer-by-layer LBR techniques or chemical modifications to build intumescent systems with it.
Intumescent? That means it swells up.
Exactly, like those fire seals on doors. When heated, it swells and forms a thick insulating char barrier, protects the cotton underneath.
And chitosan has another trick up its sleeve.
Yes. It's also inherently antibacterial. Its positive charge messes with bacterial cell walls.
Dual action.
Right. So you can potentially get flame retardancy and antibacterial properties from one base material. Studies have combined chitosan with other compounds to get FR, UV protection, and antibacterial effects. Sometimes there's a slight trade-off in fabric feel, but the potential is huge.
You mentioned smart textiles, too. Fire warning.
Yeah, combining things like carbon nanomaterials, chitosan, and phytic acid. The idea is a fabric that not only resists fire, but could potentially even trigger an alert. Still early stages, but very innovative.
How does the phosphorylated chitosan work exactly?
Okay, so PCS, phosphorylated chitosan. When it heats up, it decomposes and releases phosphoric and polyphosphoric acids. These acids act as catalysts, essentially telling the chitosan and cotton to dehydrate and carbonize, turn into char more efficiently.
So it actively helps build that protective layer.
Yes, and it takes advantage of chitosan's natural tendency to char well. The char then blocks heat and fuel transfer. Plus, the breakdown releases non-flammable gases like water, CO2, ammonia, which dilute the oxygen and further smother the flame.
A multi-pronged attack on the fire, and lots of different ways to apply it.
Definitely. LBL assembly allows for precise nanolayers of chitosan and other materials like lignosulfonate, improving thermal stability and reducing heat release. Chemical modifications, adding specific phosphorus-containing groups, have boosted LOI and helped fabrics pass vertical flame tests. Even single-component coatings based on modified chitosan are showing promise.
Chitosan seems really versatile. Now back to the really surprising one, DNA. How on earth does DNA stop fire?
It's pretty amazing. DNA has a phosphate backbone. There's that phosphorus again, which helps form char.
Yeah.
But there's more. The purine and pyrimidinases, the ATCG bits.
Yeah.
When they decompose, they release nitrogen-containing compounds and non-combustible gases like CO2 and nitrogen.
So it works in two ways, char formation and gas dilution.
Exactly. It builds a barrier and also releases gases that interfere with the combustion process, starving the flame.
What did the study show?
Really impressive results in the lab. Fabric treated with herring sperm DNA, that was the source used self-extinguished in tests, burned slowly, had a much higher LOI than untreated cotton, and didn't even ignite under certain heat flux conditions.
That's incredible. Why aren't we using it then?
Scalability and cost. That's the major hurdle. Getting enough purified DNA from biological sources for industrial textile treatment is just, well, very difficult and expensive right now. Environmentally sound in principle, but practically challenging for mass production.
The real-world barrier again. Still, fascinating science. What about other proteins? Casein, whey.
Casein, from milk, forms a decent char layer. Seems fairly durable to washing, maybe better than whey protein in some tests. Chicken feather protein, often a waste product, shows promise too, especially when combined with other things like melamine. And hydrophobin specialized proteins are being looked at as green coatings. It's another avenue of bio-inspired research.
So many natural options. Okay, let's move to the inorganic side. What's in this category?
Things like metal hydroxides, silica-based materials, nanoparticles, and those intumescent compounds again. But maybe inorganic-based ones.
Metal hydroxides. Like what?
Aluminum hydroxide is a classic example. When it gets hot, it decomposes and releases water vapor.
Cooling effect.
Exactly. Cools the material and dilutes the flammable gases. Simple mechanism, but effective.
And silica-based, like glass.
Sort of. Often used in hybrid inorganic forms. You might layer nanosilica with polymers using LBL. This can give flame resistance and sometimes added benefits like water repellency.
And intumescence. You mentioned ammonium polyphosphate, APP.
Yes, APP is a really common halogen-free IFR. It contains the acid source, phosphoric acid released on heating, a carbon source, often the polymer itself, and a blowing agent, like ammonia. It all works together to create that insulating foam char.
What about nanoparticles like clays or nanotubes?
Nanoclays and graphene can definitely enhance flame retardancy, often by creating a tortuous path that slows the escape of flammable gases and heat release. Carbon nanotubes can improve thermal stability, but as mentioned, they might sometimes hinder the swelling action of intumescent systems. It depends on the specific setup.
And metal-based nanoparticles. Zinc oxide, titanium dioxide.
Right. TiO2, MgO, SaO2, ZNO. Lots being tested. They can act as physical barriers, alter how the material degrades, scavenge radicals that fuel the fire, and improve heat dissipation.
Are they applied as particles?
Increasingly, it's nanometal oxides applied as coatings, often using sol gel methods, mainly due to cost.
Any standout examples?
Well, one study showed magnesium hydroxide significantly delayed ignition time for cotton. But A common issue with these is the loading level. You often need quite a bit of the inorganic material to get good FR performance, and that can make the fabric stiff or heavy.
That trade-off again, balance between safety and feel.
Always a consideration.
You mentioned a nanosilica intumescent system that sounded good, though.
Yes, they combined nanosilica, SiO2, polyethylenamine, PEI, and phytic acid, PA, using LBL.
Yeah.
It achieved a high LOI, low char length, good char residue, and significantly cut down the heat release rate and total heat released. And importantly, it didn't seem to weaken the fabric much.
That sounds like a win-win.
It shows the potential of these carefully designed multi-layer systems. And APP, as you said, remains a workhorse, low toxicity, effective char catalysis.
Okay, fantastic overview of flame retardants. Let's switch fully to the antibacterial side now. The traditional synthetic options, you said there were concerns.
Right. Things like QACs, quaternary ammonium compounds, triclosan, N-halamines, polybiguanides. They work, but bacterial resistance is a growing worry, especially with QACs and triclosan.
Like antibiotic resistance, but for fabric treatments.
Essentially, yes. Microbes adapt. Plus, there are broader environmental and health questions.
How do these synthetics actually kill bacteria?
Different ways. Triclosan messes with fatty acid synthesis, crucial for cell membranes. QACs are positively charged. They disrupt the negatively charged bacterial membranes. And halamines release active chlorine, which oxidizes vital cell components. Polybiguanides also disrupt membranes and cause cell contents to clump.
Sounds quite aggressive. What are the environmental downsides?
Bioaccumulation is when some of these chemicals can build up in organisms, potentially causing harm up the food chain. Some are toxic. Halogenated ones especially raise flags about water pollution, persistence, ecosystem disruption. It really drives the need for greener approaches.
Definitely. So natural antibacterial agents, plant skin, extracts, and essential oils.
A huge area, yes. Plants are amazing chemists. They produce a vast array of phytochemicals, phenolics, quinones, flavonoids, tannins, alkaloids, terpenes, many of which have antibacterial activity.
How do they work?
They can disrupt bacterial ribosomes, damage cell walls or membranes, interfere with DNA, mess up energy production. Multiple targets.
Nature's defense mechanisms. Which parts of the plant are best?
Often the leaves seem to have the highest concentration of these active compounds. Makes sense. Leaves are pretty exposed.
Any good examples for cotton treatment?
Lots. Aloe vera combined with chitosan and cinnamon oil worked well against both gram-positive and gram-negative bacteria. Extracts from chamomile, sage, green tea showed good durability after washing. Pangami leaf extract, false banana sap again, citrus peels, green lemons seem strong, tannins from piper betel leaves. The list goes on.
That's a wide range. Are any really close to replacing synthetics cost-wise?
That's the million-dollar question. Many show great promise in the lab, but scaling up production, ensuring consistent quality and potency from natural sources, and doing it cost-effectively. That's still a challenge for widespread commercial use compared to established synthetics. But the research is pushing hard.
Okay. What about using essential oils specifically? You mentioned evaporation.
Yeah, that's a big challenge.
Yeah.
They're volatile. Plus, you want a controlled, sustained release for lasting effect, not just a quick burst.
So how do you fix that?
Encapsulation is key. Putting the oils into tiny microcapsules or formulating them into emulsions or gels, often integrated with biopolymers. This protects the oil and controls its release onto the fabric.
Like tiny time-release capsules?
Pretty much. Peppermint oil emulsions showed good activity. Encapsulation opens doors for multifunctional fabrics too. Maybe antimicrobial, fragrant, even wound healing, all from one treatment.
Clever. And that gallic acid coupling method.
Another smart approach, using gallic acid to link polylysine molecules to cotton, gave it durable antibacterial and antioxidant properties. It could even be loaded with aspirin and release it slowly. Potential for medical textiles there.
Very innovative. And pre-treating the cotton. Plasma.
Yes, plasma treatment can modify the fiber surface, making it more receptive to these biofinishes. It's seen as a greener alternative to some older coating methods. One example used plasma, then a soy protein coating, which helped natural dyes stick better, and allowed an artemisia extract to add antioxidant, antibacterial, softening, and UV protective properties.
Wow, stacking up the benefits. Let's revisit chitosan, focusing on antibacterial action.
Right. As we said, its positive charge disrupts bacterial membranes' broad-spectrum activity. It can be boosted by adding metal nanoparticles or other antibacterial polymers. Combining it with N-halamines is being looked at for potent wound dressings.
And the layer-by-layer approach again.
Yep. LBL coatings with, say, polystyrene sulfonate, and silver-loaded chitosan nanoparticles, CSH, showed enhanced activity and sustained silver release without hurting the fabric's feel. Grafting chitosan onto cotton is another way to get durable effects and sometimes improve strength. It's even used in pigment printing processes to reduce bacterial growth.
Silver and chitosan seems like a powerful duo. What about other proteins? Silk.
Silk fibroin is interesting, biocompatible, strong, used as a drug carrier in wound dressings, combined with casein for controlled release. There's also sericin, another silk protein, combined with titanium dioxide nanoparticles. Applied to cotton, it gave antibacterial and self-cleaning properties, effective against resistant bacteria and helped break down stains in light.
Self-cleaning cotton.
Under sunlight, or UV, yeah. The TiO2 acts as a photocatalyst, but overall, chitosan is still the most researched protein for antibacterial cotton.
It keeps popping up. What about combining chitosan with plant extracts or oils?
Synergy again. Chitosan with eucalyptus or sandalwood oils showed improved antibacterial action. With frankincense oil, it boosted antibacterial, antioxidant, and mosquito repellent properties, plus some flame retardancy. Combining it with medicinal plant extracts enhances durability for medical textiles. It seems to be a great platform for adding and enhancing natural bioactivity.
A natural booster. Okay, nanomaterials beyond silver.
Zinc oxide, ZNO, copper oxide, CuO, titanium dioxide, TiO2 are big ones.
Yeah.
Also nanofibers, nanocomposites. The key trend here is green synthesis, using plant extracts or microbes to produce the nanoparticles, avoiding harsh chemicals.
Like that sumac leaf extract for silver MPs you mentioned.
Exactly. In-situ synthesis right on the cotton showed strong antimicrobial and UV protection at low concentrations.
And the others, titanium, copper.
TiO2 and CuO are used in cellulose wound dressings. Modified chitosan with TiO2 applied via LBL gave great antibacterial UV protection. Starch can stabilize ZNO nanoparticles. Ultrasound was used to coat cotton with ZNO and CuO using citric acid, enhancing activity against E. coli under light, likely via reactive oxygen species.
ROS, like tiny oxygen bombs.
Sort of. Highly reactive molecules that damage bacterial cells. CuO nanoparticles are thought to work via copper ion release, direct contact, and ROS generation. And another study used red sander extract to make silver-copper nanoparticles in cotton, showing broad antibacterial action.
So many nano options. Okay, the ultimate goal. Dual functional agents. Flame retardant and antibacterial in one treatment.
That's the holy grail for efficiency, yes. And interestingly, some FRs do have inherent antibacterial activity. Potassium alginate with PHMB was one example.
But chitosan seems like the star here, too.
It really does. Chitosan combined with phosphorus-containing flame retardants is a common and effective strategy for hitting both targets. Using wake shrimp shells makes it even more sustainable.
Layer by layer again.
Definitely useful for precise control. One study used LBL to build up a flame retardant and antibacterial polymer with phytic acid. It improved LOI, reduced heat release, killed bacteria effectively using an N-alanine structure, and even made it harder for bacteria to stick.
What about lignin and APP?
Covalently grafting phosphorylated lignin and APP onto cotton gave UV protection, photothermal conversion, light to heat, excellent fire safety, high LOI, self-extinguishing, durable, and antibacterial properties. Really multifunctional.
That sounds incredibly versatile.
It is. Other approaches involve self-assembled guanylyl metal complexes or polysiloxane-based coatings to get flame retardant, antibacterial, sometimes even antifungal properties. It's striking how often these sustainable solutions, especially chitosan-based ones, naturally lend themselves to tackling both problems. That feels like a real step forward.
It really does. So with all this amazing progress, what are the roadblocks, the challenges still ahead?
Durability is always a big one. Making sure these treatments last through repeated washing and wear.
Right. What else?
Cost. Developing and scaling up these new eco-friendly processes can be expensive, which can slow down adoption. Regulations are constantly evolving, so formulations need to keep pace. Consumer acceptance, people need to trust and understand these new technologies.
And making them work on a factory scale.
Exactly. Scaling up from the lab while ensuring quality, consistency, efficiency, and making sure the new treatments fit into existing manufacturing lines without major disruption. Compatibility is key.
So where should the research focus next?
Definitely on greener chemical modification methods, plasma, enzymes, more comprehensive life cycle assessments, LCAs, to really prove the environmental benefits from start to finish. Interdisciplinary collaboration is crucial. Chemists, material scientists, engineers working together, optimizing production, integrating treatments seamlessly.
Okay, this has been, wow, a really thorough deep dive. We've gone from plant saps and shrimp shells to DNA and nanoparticles, all in the quest to make cotton safer and more hygienic sustainably.
And that convergence is key, isn't it? Finding single treatments, often bio-inspired, that tackle both flammability and microbes. That shows real ingenuity.
Totally agree. And for you listening, this isn't just lab stuff. This could really impact your safer furniture, more hygienic clothes, or medical gear, and hopefully be much gentler on our planet, too.
Really makes you think.
Which leads to that final thought. As we get better at understanding and using these natural materials, these eco-friendly technologies, what other ordinary materials out there might be hiding surprising solutions to big challenges?
Yeah. What else is waiting to be discovered in plain sight? Makes you wonder.